Hi everyone! In this video, I'm going to show you how to set up and solve a system of linear inequalities. And so that's sort of fancy language for basically what we're going to do is we're going to graph a couple lines, but the difference with systems of inequalities versus systems of equations is that instead of just graphing lines and finding out where they intersect, we're going to be graphing lines and then sketching regions above or below the lines to represent an inequality. And then what you're going to end up is you're going to end up with these overlapping regions. And the section where both of the regions overlap is the solution set of your inequality space, if that makes sense. So we're going to generally have a situation where you got like a maximum of one thing and a minimum of another thing or what have you. That's going to give you different things that you're going to need to, different inequalities that you're going to need to set up. Now in this video, I'm going to do one example of modeling one inequalities word problem. And then what we're adding today is the solving step. But if you want more examples of how to model these things, I did a video last week just on modeling linear inequalities. So you can check that out too if you want some more examples of how to model these things. So without further ado, let's just jump into an example. Sam is planning her summer employment and she has 2 jobs lined up. She works at a grocery store which pays $16 an hour and she also does yard work for $8 an hour. Her student's loan won't cover all of her costs, so she needs to earn at least $240 a week all summer long to have enough saved up. But she's busy. She's taking summer school classes, and so she doesn't want to work more than 20 hours each week. So how many hours can she work each job and meet all of her obligations? Okay, so one thing that's sort of a little bit tricky about word problems is deciding which variable is going to represent what. So are we going to want to set it up in terms of money, or are we going to want to set it up in terms of hours, for instance? And do we need 1 variable, 2 variables, that sort of thing? In this question, I think the easiest way to set it up is in terms of hours. Because we've got this 20 hours is in terms of hours. And the money we can quickly turn into hours. The money per hour we can quickly turn into money just by multiplying by our wage. So I think that we're going to want hours for our variable. So let's let x be the number of hours at the grocery store. And then the other thing that we're solving for then would be, I guess, y is the number of hours at yard work. Okay. Now I've chosen x and y. X and y are really convenient because I want to solve this by graphing today. We can just sort of graph x and y in the usual way. So I guess we'll put our x-axis down here. And so x is hours at the grocery store. And y we said is hours of yard work. So let's fill that in up here, I guess. So this is my y-axis, which is hours of yard work. And we're going to need to figure out equations that relate our hours at the grocery store to our hours of yard work. So let's go through. The first one probably is, the easier one's probably this 20 hours number. So let's figure out this 20 hours number first. So she can work at most 20 hours. So what does that mean in terms of an inequality? So 20 is going to be on our right-hand side, I guess. We want at most 20, which means we want 20 on the greater than side, but it could be equal to 20 hours. At most means that 20 hours is cool. She could work 20 hours. And now we're just going to need to add together our 2 different things that she's spending time on. X is our hours at the grocery store, and Y is our hours doing yard work. We have another restriction. She needs to earn at least $240. So 240 is over here. She needs to earn at least that, which means that the money she earns, the left-hand side of this equation, has to be greater than or equal to $240. Now what we're going to need to do is we're going to need to take our x, which is our hours at the grocery store, and turn that into money. And how do we do that? Well, we are going to use our $16 per hour. So 16 times x is how much money she makes at the grocery store. And then our yard work pays $8 an hour. So that's 8 times the number of hours she works on the yard. And both of these equations we're going to want to rearrange into y equals mx plus b form. This first one I can sort of basically just do in place. All I need to do is just, bring this x over to the other side. So y is less than or equal to negative x plus 20, I guess in y equals mx plus b order. And if we go to graph that, actually let's get the other equation first to see how far we need to go up the y-axis. So this other equation I guess I'll do in orange. First thing I'll do is I'll bring the 8x to the other side, or 16x, sorry. So 16x on the left becomes negative 16x on the right, plus 240. And then I'm going to divide by 8. Now, be careful anytime you're dividing an inequality, of course. You need to be very careful. Sometimes you need to flip your inequality. In this case, we're dividing by a positive number, so we're okay. Positive numbers you don't need to worry about. And 240 divided by 8 is 30, right? Yeah, because 3 times 8 is 24. Okay, cool. So actually, I'm going to graph this one first because it's got the higher y-intercept. Now, I don't have 30 boxes here, so I guess I'm going to do 2 per box. I guess I'll label that in green. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Ran out of room. 28 and 30. And this is yard hours. Okay, cool. And I've got negative slopes for both of these, so I'm not going to go above 30 for sure. Now, we could do one per tick on our x-axis, and that would be fine. But it's actually, there's sort of like a graphing hack that you can do. If you make your x-axis and your y-axis the same scale, so if I make this 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, well, then that means that when I'm graphing my slope, it's just going to work out because a box horizontally is 2 units and a box vertically is 2 units. So I can just draw my slope the usual way and it'll just happen to work out nicely for me. So I'll show you what I mean right now. So my y-intercept for this orange line is 30, right? So 30. And then a slope of negative 2 means I should be going over 1 down 2. So like if I'm actually doing like 1 per box, or like 1 across, that's like half a box over and then 2 down. But if I just do 1 box over and 2 boxes down, that's actually over 2 and down 4. According to my y scale. But that's actually the same slope. Because I've done my x and my y-axis at the exact same scale, it actually makes graphing the slope really, really easy. I can just graph it the usual way. And since it can be equal to, right, it can be equal to, I can graph this with a solid line, as I showed you guys last video. Now, for the sake of not making this graph super confusing with shaded regions all over the place, I'm only going to shade right at the end. But if we wanted to, we want y greater than this, we could shade everything above this line. And that would be fine too. But I think it just gets a little bit too confusing with shadings all over the place. So the other graph, we're going to have 20 as our y-intercept and a slope of negative x, means over 1 down 1, over 1 down 1, over 1 down 1, and so on, over 1 down 1, all the way over here. And again, it can be equal to, so we're going to do a solid line. And of course, if it had to be exactly less than or greater than, not equal to, we do a dotted line in this case. So now I think I'm going to just shade my solution region all at once. I need y less than this, so I need below this line. And I need y greater than or equal to this, so I need y above this line. So above the orange line, but below the blue line, means that my only region is this region down here. Okay. So now all we need to do is just pick our solutions out of this graph. So like there's lots of possible solutions. This one's the furthest left we could go. And this point here is 10, 10, right? So 10, 10 isn't very exciting because that means our x is 10 and our y is 10. So it's 10 hours at the grocery and 10 hours at the yard work. Okay, and that's, 10 and 10 is kind of boring. They're the same. Let's pick one where they're a little bit different from each other. Let's pick maybe not a point on the line. Let's pick a point right in the middle of the region over here. That point there is 16 in our x-axis and 2 in our y-axis. So that's x and y. So this would be 16 hours at the grocery and 2 hours at yard work. Right, and so on for all of these points in this region, right? You could go all the way over to here, you could go all the way back to here, up to here. You could pick a point that's actually an integer value, but it looks like it's not, because that would be 13 and 7 if we go with sort of the half boxes. Anything at all in that entire sort of triangle counts as our solution space. Okay? So I wish you success with modeling and solving these things, and let me know how it goes.